very last speaker today is Paul Raftery. I apologize, we are running a little bit over, but I appreciate your attention to Paul. Plus, he brought a prop.
Right? I brought a prop, of course, which always helps. Right. So my name is Paul Raftery. I'm a staff researcher at the Center for the Built Environment in UC Berkeley. I'm going to talk a little bit today about the Changing the Rules project that we have. I realize it's pretty late in the evening and you've been here all day, so I'll try and keep it quick and interesting. Just to give you a small bit of background before I move on to the fun stuff, it's a 3.5-year long project that started last year. It's funded by the CEC. The total funding is just under $2 million. And the main kind of areas that we're looking at here are personalized comfort systems and optimizing HVAC equipment in large office buildings. We plan to do some of that work, do some developmental testing, and then put it into demonstration sites and update codes and standards accordingly. There's a big project team on this, a large group at the CBE under Ed Ahrens. The CIE is involved with Carol. I don't think he's here at the moment. The EECS department, David Culler and his work in SMAP is involved, and Taylor Engineering as well, our design HVAC firm in the Bay Area that we've worked with before. So now, the first main area of this is personalized comfort systems. I realize that everybody's kind of from a different perspective here, so just to give some background, in a typical multi-user space in a building, about 5% of the people will be dissatisfied with comfort. And that's the best you can possibly do under laboratory conditions, and it's partly idealized. In a real building, it's typically about 20%, and that's reported user satisfaction with comfort in their offices across a wide range of sources. So this really is a genuine problem, and the only way to solve it is to provide some measure of personalized control over your local environment. And now, of course, the prop. So we built a heated and cooled office chair that runs off a battery pack. It's been patented and licensed to a manufacturer in the Bay Area. It uses ultra-low power, 10 watts in heating and 4 in cooling, and the battery will last about a week. And the major part of this project is to incorporate some onboard sensing in the device, so we can measure temperature, occupancy, and actual user preference for heating and cooling, and report that over a wireless network. We may even then be able to control the HVAC system according to the reported user comfort. So if you're asking for more cooling, you can turn down the thermostat. If there are multiple users in the space and they're all asking for more cooling, you can also turn down the thermostat. And this is important from more than a comfort perspective. Based on the human subject testing that we did at CBE, we found that people had the same or better reported comfort using this device over a much wider range of ambient air temperatures. So that tells us that we can actually set back the thermostat, expand that deadband between the heating and cooling set point, and save approximately 5 to 10% per degree Fahrenheit that we expand that range. So there are really large energy saving implications from this. This is actually one of the very basic versions of the chair because they're actually all out on field studies at the moment. So the other interesting thing is that there's lots of devices that are used for personal comfort, those little foot warmers, the convective heaters, but there's no standard for actually measuring how well those devices perform, just doesn't exist. This project was actually in part to develop that standard and a classification method. So you can see a couple of those different devices here. And what we did is we developed a standardized method of test where we can measure the amount of heating effect each one of those devices had on a thermal mannequin. That device there actually uses thermopiles to the mannequin, the human-looking object, uses thermopiles to measure the heating effect that actually these devices give. And we tested each one of those devices and developed a ranking. So you can see the convective-based devices don't actually perform well. They're effectively just heating the environment and incidentally heating the person. They typically use anything from 100 to 1,500 watts, and they have a very small effect on the actual person. The radiant-based devices do a little bit better, but they're still nowhere near as useful or as effective as the conductive-based devices, because basically with those devices, all of the heat goes into the person. So that's the kind of first major area of this project. The other one is on the actual building itself. So it's looking at the HVAC controls in the building and trying to optimize those. So what we focused on were large office buildings and the typical HVAC systems that are in those, which is variable air volume air systems. And we've developed optimization methods to control those directly. And then there's some integration with the other part of the project, which is looking at new ways to control the space temperature set points, setting them back using the personal comfort systems to provide improved comfort, controlling them based on adaptive clothing models that predict the type of clothing that people will wear based on historical outside air temperature, and actually a new product called Comfy, which is developed by Building Robotics, which is a startup company with students from UC Berkeley, both in the EECS department and in CBE. And that product is actually running in Cedar July Hall right now, along with the optimization. So, sorry there. So we're doing this using the SMAP software that David Culler developed, and that basically communicates with the BACnet in a building and allows us to control devices within the building. So as I mentioned, we developed code for optimizing VAV control strategies, and we also developed some automated fault detection and diagnosis methods. So I'll talk about that first, and then I'll give you a demo. Hopefully it'll work. So what we did in this, and this is in Cedar July Hall actually, was the first test site for this. We looked at the building management system on a zone-by-zone level, and then we analyzed the data to determine if there were faults in that particular zone. And we can identify things like problems with ventilation rates, broken damper linkages, problems with a thermostat, zones that are constantly reheating, and zones that are kind of limiting the amount of optimization we can do at the air handler level. So on the first floor of this building, we ran it, and I worked with Domenico, who's the building manager, to identify faults and root cause the actual faults. So we ran the algorithm, identified the faults, and then checked the actual physical devices. So in some of these zones, you had thermostats that were directly over a heat source, so obviously we're reading very incorrectly, or damper linkages that had come off the damper, so the damper was actually fully closed for the air unit. And then the other thing we looked at was the optimization of the VAV control for the whole building. So for an air handling unit in a building like this, it basically supplies air at one temperature and one pressure for the entire building. And the choice of those two set points drives the energy use of the whole building. There are some limitations on it, but in a typical building, they're usually just fixed set points that are set to maximize the amount of comfort as best as they can without too much concern for energy. Sometimes they kind of do a little bit of a reset based on the outside air temperature, but typically they're fixed. I'll see if that works. So this is actually running the building live as we speak. Exactly what I thought would happen did happen. Fortunately, I prepared this slide here. It's a little bit better. So as I said before, we implemented this reset strategy. The building was running with a fixed supply pressure set point of 1.4 inches of water. And this is what's happening in the building right now. We're controlling that pressure set point to meet the demand as it's measured in the building. And you can see all of this white under that red line is energy savings for this building. The trend on the top is the amount of pressure requests, and that's how we actually determine this optimal set point. So we look at every zone in the building on a 1-minute time step, and then we assess whether or not that zone has enough air going to it. If it has enough, then it's not going to drive the pressure set point. If it doesn't, then we increase the pressure set point accordingly. And now the same thing happens for the supply temperature, and there are interactions between those two, and there's more work to be done to actually identify the actual optimal set point for both of those two strategies, and that's the next stages of this project. But the really interesting thing about this is the system that's used to control almost every large office building in the United States. VAV systems are prevalent since the 1980s, and BACnet controls are prevalent since the 90s. So if you go into an existing large office building that was built in the last 20 years, you could retrofit this in independently of the building management system at really low cost. So the energy savings potential for a product like this are enormous. And that's just the first of the optimization strategies that we're looking at in this project. Hopefully we'll be developing and testing many more in Cedar July Hall over the coming remaining 2 years of the project, and actually running these in full demonstration sites where we can very clearly quantify the amount of energy savings that we generate from this project. So that's pretty much the end of my talk, but I realize it's the end of the presentation, but I'll leave the chair up here if anybody wants to give it a try, see what it's like. If you have any questions or comments or things you might think might interest us, please feel free to get in touch with either me or my colleague Fred, and there's more information on our website.
Any questions for Paul?
Do you also use CO2 sensor to control the airflow?
So in smaller areas, and this is becoming more prevalent in modern buildings. So if you look at conference rooms, which are rooms that are like intermittently occupied but with high number of occupants, then it actually makes sense to measure the amount of CO2 in the room and control the ventilation accordingly. But for smaller office spaces that are more regularly occupied and less densely, it doesn't make sense to do that. And actually, a lot of what drives the ventilation requirement, particularly in California, is the ventilation per square foot, which is fixed regardless whether there's 1 occupant or 10 in that space. So that becomes the ventilation minimum in those types of spaces.